Alright guys, in this video we're taking a look at writing the name for an ionic compound when given the formula. Quick reminder, when we say ionic compound, what we mean generally is you're going to have a metal plus a non-metal. Look at a few examples. First, we have AlCl3. This one's really easy. All you do is you write the name of the positive ion, Al. You can find on the periodic table that is aluminum. And then you take the ending chlorine, Cl's chlorine. You always change the ending of an element to "ide." So chlorine becomes chloride. So that is simply aluminum chloride. And we don't pay any attention to the numbers in the formulas unless we have to show the oxidation state of a transition metal, which we'll see in a minute. CaCO3. Again, Ca is just an element. It's calcium, so we write its name. Now this right here, if you get past that first element and you see that you have multiple elements together, that means that this has to be something from the polyatomic ion list. Don't try to write something like calcium, carbon, oxygen. If you get past that first element and you get a group of elements, you need to go straight to your polyatomic ion list. We're looking for CO3. You see that right here we have CO3. The name of that thing is carbonate. So this is just calcium, and then you name the ion, carbonate. Never change the ending of a polyatomic ion. Okay. In the first example, we had chlorine and we turned it into chloride. We do that with something from the periodic table. Don't do that with a polyatomic ion. If you look at the list and it says carbonate, it's carbonate. You would not change that to carbonide. Fe2O3. This time we have something that is on the periodic table in the transition metal area. So we're uncertain as to what the oxidation state is. Iron can either be a positive 2 or a positive 3. So we need to denote which one this is. So we go ahead and write the positive ion, iron. Leave some parentheses to put our Roman numeral. Oxygen is the negative ion. This becomes oxide. Now it's just a matter of determining what the charge of iron is. Well, the shortcut, whenever neither subscript is a 1, you can just uncrisscross them. Okay? The 2 on iron was the negative 2 charge that came from oxygen. That means that the 3 on oxygen was the positive 3 charge that came from iron. This time we have something from the transition metals, manganese right next to it, so we have to show the valence. Manganese can take as many as 5 different oxidation states. So manganese. But the difference is where both of these were not 1, here manganese, there's only 1 of them, which means that we don't know if this was reduced. We're not sure if this is uncrisscrossed 3, or potentially this could be a 6 if this was reduced. So we work it out. But first, let's just set it up. Manganese something oxide. Okay. The way you work out the charge is you realize that manganese oxide has 2 components. It has manganese, which is the positive ion, and oxygen, which is the negative ion. Okay. So we find the charge of oxygen, the negative ion, it's a negative 2. And we say that in manganese oxide, what I have is 1 manganese atom with 3 oxygens. Okay, this is MnO3, and we said that each one has a negative 2 charge. So the total on my negative side is negative 2 plus negative 2 plus negative 2, or 3 oxygens times a negative 2 charge. I get a negative 6 charge. So in order for this to be a neutral compound, I have to have the same positive charge as the overall negative charge. So here, I know that this has to be a positive 6 over here. Okay. So I have to take a look at how many atoms of manganese do I have. Okay. I only have one atom of manganese. So the only thing that that one atom could be is a 6. They have to be the same. This entire positive 6 charge has to come from here. Okay. What if this had been Mn2O3 instead? What if it was Mn2O3? Well, I would have done the same thing. I would have said that that's a negative 6 charge over here, and I know that I need a positive 6 charge over here. But instead, I would have realized that I've got 2 atoms of manganese, so positive 6 split between 2. Each one of these would have been a 3. This would have been manganese 3 oxide, which differs from manganese 6 oxide. Okay. So let's take a look at one more example. We have PbSO4. So again, we realize that we have to show the oxidation state of lead, so we just write its name down, lead, parentheses, then SO4. Take a look on the polyatomic ion list. You find SO4. SO4 is right here. That is sulfate. Never change the ending of a polyatomic ion. Okay. So there are no subscripts here, and there's a 1. Lead's a 1. So we have to determine what the charge is. Well, I have 1 sulfate. This is not. That does not mean 4 sulfates. Okay, I understand that it ends in a 4, but SO4 is sulfate. The whole thing is. The only way I could have 4 of those would be if I had this. That is 4 of these. This is 1 of these. So that's not 4 sulfates, that's 1 sulfate. You have to have the S and the 4 O's to make a sulfate. So if we look on the polyatomic ion list, we see sulfate is a negative 2. So I know that I've got 1 sulfate and it's a negative 2, so my entire charge on my negative side is a negative 2. I know that my entire positive charge has to be a positive 2 so that they'll cancel each other out. Well, how many leads do I have? There's only 1 lead. So if I've only got 1 lead to come up with that whole plus 2 charge, this has to be lead 2 sulfate.